Hi guys, welcome back to the channel. Today we'll be training a neural network from scratch to build a NeRF, or neural radiance field. Using this beautiful intersection of modern-day deep learning and classical computer graphics, we can turn these static 2D images into this 3D scene. NeRFs are able to take images of an object or scene from various angles and learn to synthesize new perspectives that haven't been seen before. NeRFs unlock a whole new way of creating virtual objects and worlds, and brings us a step closer to tying our digital worlds with reality. The fascinating part is that the code to implement a basic NeRF from scratch isn't even that complex, and only requires some basic introductory knowledge of machine learning and calculus. Implementing this with PyTorch is going to be a breeze. NeRFs are an amazing project for those that have already taken an introductory machine learning class and want to get some hands-on experience with the subject matter, or for those that want to be introduced to computer graphics. In fact, on my M1 MacBook Air, this model only took a couple of hours to train. No beefy GPUs required today, although having one definitely wouldn't hurt. As usual, all of the code from today's video and instructions on how to run it will be linked in the description down below. While the original NeRF paper was published in 2020 and may be considered even old by some in academia, it's been a portal into a whole new world that's still being explored today. In fact, you guys might have already used the NeRF even if you hadn't realized what NeRFs were. Take Google Maps for example. If we visit an iconic location such as, let's say, the Golden Gate Bridge, click on it, and then hit this immersive view, we can see that Google has this 3D environment for us to explore of the location. I mean, isn't this so cool? You can zoom out and see all of San Francisco virtually from the palm of your hand. And you guessed it, Google was able to create this for us with the magic of NeRFs. So what exactly is a neural radiance field? Well, a radiance field is simply a field of really small points in 3D space, where each point has a radiance, or a certain amount of light energy traveling through it in a specific direction. The neural part is introduced because we want to train a neural network to be able to estimate the radiance of each point in our scene. So while the car may look solid, it's actually just a bunch of points of light that our neural network has estimated. The task for our network today is given the 3D coordinates of a point in our scene, it needs to estimate how much light energy is at that point, which is defined by color and transparency. What we need to give our network is a bunch of images of an object along with each image's pose data, which consists of the camera's position and angle. Then, for each pixel of each image, we shoot a ray from the camera through the pixel into the scene and sample points along the ray. Next, we use volume rendering to accumulate these samples into an estimate of the pixel's color. Repeating this for all of the pixels in an image yields us a prediction. Finally, we compare this resulting image to the original one in our dataset. Because volume rendering is trivially differentiable, we're able to easily calculate our loss and perform gradient descent so our network can learn. This is just a high-level overview, so don't worry if it doesn't make perfect sense just yet. We're going to dive deeper in a sec. As with any machine learning problem, the goal of training our network is to be able to generalize to data, or in our case, camera poses, that the model hasn't seen before, so we can generate new images of the object. In order to be able to synthesize new views, our network needs to learn about depth and perspective simply from 2D images. To fully understand what's going on here, let's just take one ray that's been sent into the scene. This ray represents one pixel from one image in our dataset. The image already tells us what color the pixel should be, which is our ground truth. Naturally, we're hoping our estimate of the color is as close as possible. For every point along the ray, we need to answer 3 questions. First, will the ray reach this point uninterrupted, or will it have hit an object by now? Second, assuming we do make it to this point, what is the density of the object at this point? Is it empty space, a translucent material, or a solid object? This determines how likely the ray is to terminate at this point. And finally, assuming we do make it to this point and the point is not just empty space, what is the color of this point? Since we're in a continuous space, there are an infinite amount of infinitesimally small points along each ray. But answering these questions for each ray shot into the scene is what's necessary to use our neural radiance field for volume rendering. Another way to think about this is that the color of a pixel is a function of all of the points in the radiance field that lie along the path of the ray sent from the pixel into the scene. However, it wouldn't make sense to accumulate the color of all of the points in our radiance field along this path because some points will be completely occluded, so we don't want them to contribute to our final estimate of the pixel's color. Given that the Cybertruck is made from stainless steel, it's highly unlikely that we'll be able to see anything behind those steel parts. Also, the translucent parts, such as the windows, will tint the other points that appear behind them, which is also something we want to consider. Let's quickly go through an example with the iconic scene from Harry Potter and the Chamber of Secrets, where Ron and Harry fly the Ford Anglia to Hogwarts. Say this is our camera pose, and we shoot a ray through this pixel at the car. From the side, this is the path our ray would take. For simplicity, let's just say there are 3 objects along the path of this specific ray: the windshield, Ron's flaming orange hair, and the baby blue of the car behind them. Our ray will look like this. What we know is that our ray will make it to the windshield because that's the first object along the path. Nothing is in the way. Then the ray marches through the windshield to Ron's hair. Even though the windshield is transparent, it still reflects or absorbs some light, which slightly tints the hair. Finally, because Ron's hair is solid, it completely obscures the part of the car behind him. After considering these observations, the color of each point might look like the following. The density of each point is represented by that dot's transparency. To get the final color of our ray, we can simply composite these points from the perspective of the camera. The blue is completely occluded by the orange, and the orange is slightly tinted by the presence of the windshield. Each of these 3 coordinates along our ray will be an input to our neural network. Remember, the input is just a 3D point in space. The output of our network will be 4 numbers, an RGB color represented by the first 3 numbers, and the density represented by the 4th. You might be now wondering, how do we combine the densities and colors of the points to yield us images of our object while accounting for occlusion and transparency? Well, we need to dive deeper into volume rendering. Let's try to make things more palpable with some equations. Don't be intimidated here. This function just tells us the final color given a ray. Remember, our neural network is simply a part of this integral. Our ray is defined by an origin point and a direction that is parameterized by a variable t, which conventionally represents time, although there's not really a temporal component to our NeRF. The bounds of our integral is a near plane and a far plane that we define. We want to make sure that our object is within these bounds, and we want to limit all of our calculations to this range for each ray just for the sake of performance. Inside the integral are 3 components, and you guessed it, each component is an answer to each of our questions. The first component, t, is our accumulated transmittance from our near plane to a point along the ray. This is essentially the probability that our ray is able to travel to a point without being obstructed by anything else beforehand. The second component, sigma, is our density. The density is a differential probability that our ray terminates at this exact point due to it getting blocked by something. What's interesting here is that the accumulated transmittance at a point is a function of the density of all of the points that come before it on the ray. This makes intuitive sense because if a point earlier in the ray's path has a higher density, there is less likelihood of the ray making it to the current point. So we have 2 probabilities that we talked about, which might get a little bit confusing, but I just wanted to clarify that the density of a point is the probability that the ray terminates at that point. Maybe it runs into Ron's hair or the side of the car. The accumulated transmittance is the probability that a ray even makes it to that specific point, which is the same as saying the probability that it doesn't get terminated at any previous point along the ray. The accumulated transmittance of the car behind Ron is low because the density of Ron's hair is high, as the hair is a solid object. What we see on screen is that the transmittance is a function of all of the densities that precede it. The third component is our color, which is a function of not just our ray, but also our view direction. This makes sense because if a material is reflecting light, its appearance changes as we view it from different angles. However, for today's implementation, we'll be setting aside view direction just so we can ensure we grasp the fundamentals first. Each of the answers to these questions can be represented by a number, or 3, in the case of color. If we simply multiply those numbers and integrate across all the infinitesimally small points along the ray, we will get the exact color of the pixel from where the ray originated. Solving this integral exactly is impossible. That's why we'll be using a numerical method instead, kind of like what we did in my Monte Carlo integration video. However, today we'll be using a stratified sampling method, where we divide the ray into a set number of bins. Then we uniformly choose a point in each of those bins to contribute to our final estimate of the ray's color. Here are our new equations. T sub I is still our transmittance at point I along the ray, and C sub I is still our point's color. But because we've now discretized our space, we now have a sigma times delta term. We're essentially taking our estimate of the density at point I and multiplying it by delta I, which is the distance between samples I and I plus 1. I'll be referring to 1 minus e to the negative sigma I delta I as alpha. The transmittance equation shown on screen is what was provided in the paper. However, if we want our transmittance to be directly a function of our new alpha term, some simple algebraic manipulation yields us the following equation. This value is exactly the same. We've just used some algebra to move some things around. When sigma times delta is high, our array has a higher chance of terminating, and vice versa. Note how t sub I is still a function of our sigma times delta term. Let's take a look at the graph of e to the negative x, which is a part of our transmittance function. When sigma times delta at point I is high, it lowers the transmittance value for future points along the ray, which in turn means that future points along this ray will contribute less to the final color. Conversely, it increases the value of 1 minus e to the negative sigma times delta, which means point I itself will contribute more to the final color. I know that was a lot, but just a quick recap before we jump into our dataset and then the code. First, take an image and its pose from our dataset and shoot rays through each of the image's pixels. Second, we take stratified samples along our array. Third, for each sampled point, we have our network predict its color and density. Fourth, with each point's color and density, combined with the accumulated transmittance, which is the density of all the points that came before the current one, we determine the color contribution of each point along the ray. Fifth, we sum up the contributions of each point to result in our final estimate of the color of the pixel that the ray was originally shot from. Sixth, once we have the estimated colors for each pixel in our image, we compare our generated image with the ground truth from the training dataset. Then we calculate the loss, and with the magic of differentiability and calculus, perform backpropagation. And finally, we repeat this for all of the images in our dataset. Let's now briefly talk about the dataset and how I created it. This is what our synthetic data will look like. Each image is 100 by 100 pixels. The way I created this dataset was by importing a Cybertruck model into Blender and using a small Python script to place evenly spaced cameras around the object. Then I simply rendered each camera's image and stored the pose data in a JSON file. I'm not going to dive into this code specifically in the video, but I'll leave it in the GitHub repo. Obviously, using a 3D model to create images for a NeRF is pretty redundant, but the reason for using synthetic data is because we can easily get the pose data for each image. Don't worry though, the core concepts of NeRFs still remain relevant regardless of the dataset. It is possible to generate the pose data simply from a series of images of a real object. I'll leave the NVIDIA Instant Neural Graphics Primitives repo linked below as well, which is what I used for the Tesla and Lego set examples. The code to create our dataset class in PyTorch looks like the following. I've already pre-packaged the images into a NumPy NPZ file, which is also included in the repo. There's nothing too complicated going on here, as we're simply extending the dataset class defined for us by PyTorch. We simply load in the data from the NPZ file and pull the images, poses, and focal length from it. The near and far planes for this specific dataset are at 3 and 7. This means the Cybertruck is at least 3 meters away from each camera, and its furthest point is less than 7 meters away from each camera. The images for this dataset, like I mentioned previously, are 100 by 100 pixels, meaning the tensors representing our images will be 100 by 100 by 3. Keeping it small will speed up training and still allow us to fully grasp the concepts behind NeRFs. Feel free to make your own dataset with the code I used in Blender and a 3D model of your choice. The length of our trained dataset will be 105 and our test dataset will be just 1. I'm following the tiny NeRF example offered in the original paper's code. Finally, whenever we fetch an item from our dataset, we will get back the image data at that specific index value, the 4x4 tensor for the pose data, and the focal length, which is the same for all images in the dataset, as all the pictures were taken with the same camera parameters in Blender. Now, let's quickly take a look at the pose matrices. Each is a 4x4 matrix. Imagine each matrix as a portal that transforms points relative to their own origin to the coordinates of the 3D world. We can move, rotate, and scale points or vectors easily with matrices. The top left 3x3 submatrix is responsible for rotations and scaling, so if we only wanted to apply the non-translation transformation, these 9 numbers are all we need. These 3 values are responsible for translation. The origin always gets mapped to these 3 coordinates, and all the other points are translated relatively. If we wanted to apply the entire matrix at once with a 3D point, we append a 1 to it. After the multiplication, we divide all the coordinates by the 4th value to ensure it remains a 1. These are called homogeneous coordinates. I encourage you to look more into them if you have any questions. Let's take a look at the pose matrix from this training example. Imagine I have this camera at the origin looking down the negative z axis. It has a center and 4 vectors coming out of it to signify the direction it's looking in. First, we move the origin to the new origin defined by the 4th column. Multiplying the rest of the vectors by the pose matrix shows us the rotation that was applied. Now, if we take a look at the image from our dataset once again that was associated with this matrix, we can see how the perspectives seem to align. I'm not going to dive deeper into the theory behind transformation matrices and what each number does in this video, but if you'd like to learn more about transformations in computer graphics, I'll leave some of my favorite resources down below. Before we jump in, I just want to quickly note that I'll be implementing the simpler NeRF model that the authors of the paper shared. So if you've already read the paper and get confused about why I'm leaving some parts out, I want us to grasp the fundamentals first. For today, we need to implement our neural network class, 2 functions specific to NeRFs, and finally, our training loop. Let's dive into the code for our neural network now. We extend torch.nn.module to create our MLP class. There are 9 total layers, with all of them being simple linear layers, and all but the last one being followed by ReLU activation functions. The 5th layer, or the first layer in the second block, has a skip connection for the inputs. That means our network takes in our inputs twice. Once at the beginning and once in the 5th layer, where we concatenate the inputs with the activations from the 4th layer. The forward function is trivial. We simply pass the inputs through the first block, concatenate the output with the inputs again, and then pass that through the second block. Taking the output of the final layer, we pass the first 3 numbers, the ones that represent the network's color prediction, through the sigmoid activation function to limit it between 0 and 1. And the 4th value, the density value, through the ReLU activation function. Let's now hop over to our first function specific to NeRFs, the getRays function. This function returns the ray origins and directions for the rays passing through each pixel. We first create a mesh grid to signify the x and y coordinates of our image. Then we center the points by subtracting by half the width and height, followed by scaling the x and y coordinates by the focal length. In computer graphics, using z equals -1 is simply the convention. Let's dive deeper into what exactly is happening. Imagine these blue dots are the points we get from our mesh grid. We're currently looking down the -z axis. Each blue dot represents the center of a pixel of our image, which in this case is 2x3 pixels. Let's start off by centering the points and then moving them down to z equals -1, like we saw in the code. In this example, let's assume the focal length is 3, which represents how far away the image plane is from the camera's origin. Then, dividing by the focal length scales the points inwards. These blue points represent the directions our rays will take, starting at the origin. If we extend the rays from the origin to the camera plane, we see that the rays go through each of the blue points. However, since they're direction rays, we need to normalize them to length 1. Finally, we need to multiply the origin point and the direction vectors by our transformation matrix. If you recall, the transformation matrix will transform our camera from the origin to the correct location and orientation in 3D space. Revisiting the function, we normalize the directions and transform the direction vectors along with fetching the new origin from the transformation matrix. We don't translate the direction vectors because they don't represent a position in 3D space. The function ends with us returning the new ray origins, which are the same for all the rays, and the new ray directions, which take into account the relative position of each of the image's pixels. Since each origin and direction is represented by 3 coordinates, the dimension of each return value will be the height of our image times the width of our image times 3. Let's now write the function that actually performs volume rendering with our model. The goal of this function is to take the neural network, the ray origins, ray directions, near and far planes, and the number of samples to generate an image. Remember that the pose data is baked into the ray origins and directions because we use the transformation matrix to generate those values. Let's start off by generating the samples along each ray. We want to stay within our near and far planes, which are unique for each dataset. We then broadcast the vector to match the dimensions of our image. Each pixel of our image gets n samples. Next, we stratify our t-values by a little bit so we don't sample the same points every time we use this image for training. This makes our network more robust. Each pixel gets its own set of randomly sampled t-values. After we have the t-values we want to sample with, we calculate the actual points in 3D space where each sample lies. So we multiply each t-value with the ray direction and add the product to our origin. This is just how our ray equation is parameterized. We're working with 4D matrices here, but I find it easier to think in terms of 2D, because our image is 2D. As you process the dimensions of each tensor we're manipulating, don't try to visualize what a 4D tensor might look like. Just imagine each pixel in our 2D image having, let's say, 64 samples, and each sample is represented by 3 coordinates. While this may sound trivial, I really do find it easier to think about our 2D matrix, which is the same shape as our image, being made up of 2D matrices in the shape of number of samples by 3. The order of these dimensions will remain consistent. First is always height, then width, then the number of samples, and then the points in 3D space. Now that we have all of our points, we can pass these points into our network. Since the dimensions of our input is height times width times number of samples times 3, we want our RGB variable to be height times width times number of samples times 3, and our sigma or density variable to be height times width times number of samples times 1. Next, we perform volume rendering along each ray. Remember the discretized equation that we're implementing. We first calculate the distances between each consecutive sample, resulting in a tensor of shape height times width times number of samples. Next, we calculate our alpha values, which is our middle term in the discretized equation. Using these alpha values, we can easily calculate our accumulated transmittance with the exclusive cumulative product, which unfortunately PyTorch doesn't natively support. This means we perform a regular cumulative product and then shift the values over by 1, appending a column of 1s at the beginning. If you recall, the original equation has a summation, but because the alpha values are already exponentiated, the algebraic equivalent is to simply multiply them. Multiplying our alpha values with the accumulated transmittance yields us our weights for the colors at each of the samples. We then multiply the weights by our colors and sum them up along each ray, resulting in a final tensor of shape height by width by 3. Wow, that was a lot, guys. Thanks for pushing through. I think the biggest challenge with any machine learning library is keeping track of all of the dimensions of all of our tensors. That's why I've tried my best to make the dimensions as clear as possible. And again, don't forget the semantic meaning of each dimension. I found that to be tremendously helpful when juggling all of these different tensors. Now for the final piece of code, the training loop. Render rays was the most complicated function, so we've gotten past the hard part. After our imports, we set up our train data loader along with the data point we'll be using for testing. Then we initialize our model, optimizer, and loss function. Today we'll be using the atom optimizer and the mean squared error loss function. For each epoch, we iterate through our train dataset. After zeroing our optimizer, we send the target image, pose, and the focal tensors to our GPU. Then we get the rays for that specific pose matrix. Passing in the origins and directions along with the other necessary parameters to render rays yields us our predicted image. We can use this predicted image and our target image to calculate our loss. Then we simply backpropagate the loss to calculate our gradients and then take a step with our optimizer to update the weights of our network. At the end of each epoch, we turn off the gradient calculation and pass our test pose into our network to see what the generated image looks like. After 10 epochs of training, we can see that... Wait, what? Why is our Cybertruck just a giant blob? Well, there is one final piece of the puzzle that we need to discuss. Positional encoding. The issue is that our network is still having a hard time making out the finer details of our Cybertruck, or the high frequency features. I mean, there's not really much complexity to the shape of the Cybertruck anyways, but let's give our network a break here. It's trying its best. So what do we need to do? Neural networks are naturally biased towards learning low frequency functions. Well, the authors of the paper proposed taking in the input coordinate and mapping it to a higher dimensional space. So we need to morph our 3D input to a 20 or 30 dimensional input. However, we don't want to just scale our input by an integer number. This doesn't really add any value to our network. What the authors did was use the sine and cosine functions while raising the factor that the input was multiplied with by a different exponent. The sine and cosine functions infuse higher frequency information into our input before passing it into our network. L is a hyperparameter that determines how much high frequency to add. Well, how do we implement this? Thankfully, all we need to do is make a small modification to our network class. We add a new parameter to our constructor to take in the embedding size that we want to use and calculate the size of our new input. Each of the 3 points of our original input has both the sine and cosine functions applied to them, L embed number of times. We also include the original points as part of the input, hence the 3 plus 2 times 3 times L embed. We then write this little encoding function that takes in our input of 3 values and returns a new tensor that's been mapped to the higher dimensional space. With the embedding size of 6, our new input is now mapped from a 3-dimensional space to a 39-dimensional space. Finally, in our forward function, we first pass in our 3D input through our embeddings function and propagate it forward through the network like normal. All the other code actually remains the same. Let's rerun our training loop. Whew! It looks like our network is properly able to synthesize new views of our Cybertruck. I've also included the code I've used to generate the animations of the Cybertruck spinning in the repo. There's one final magical property of NeRFs that I want to briefly touch upon. Compression. The PNG files, which perform lossless compression on our images, take up a total of 1.73 megabytes. However, a single checkpoint of our model, which remember has the capability to generate as many images from as many viewpoints as we want, takes up just 1.77 megabytes. We've not only encoded all of the image data into the weights of our neural network, we've also encoded the ability to generate new ones as well, for essentially no additional disk usage. Well, there you have it guys, the magic of NeRFs. There are a lot of other topics that I didn't get a chance to cover because of time, but would love to if you guys want. One thing the paper talks about is having some sort of view dependence, which essentially bakes in the lighting information of our scene into our NeRF model. This is really useful to see the specular highlights of any reflective materials in our scene. Another optimization the paper covers is hierarchical sampling. This allows us to take samples where we think the object actually is, rather than waste compute by taking too many samples in just empty space. Additionally, if you want to use your own data, such as with pictures from your phone, you would need a way to compute the poses from those images. Thankfully, there are open source libraries such as CoolMap that can help with that. Remember guys, we talked about the first paper in the world of NeRFs. In the past several years, so many new advancements have come out, like combining neural rendering with traditional rasterization or Gaussian splatting, both techniques which provide massive speedups. In fact, there's also research being done on how to create a NeRF with just one image. If you guys are interested in learning any of the advanced optimizations for your NeRF or how to use your own data, please let me know down below and I'll get right to work on part 2. But thanks so much for watching, and until next time, bye-bye.